This one?
Yeah.
Yeah, we know that for ideal gases, the kinetic energy is equal to 1/2 URMS squared. And so if they have the same speed, but there's one other variable that we have to worry about. And what would that variable be? The M, right? So the common thing that comes up is that, if like the nitrogen in this room is moving very fast, but it depends on M because nitrogen doesn't weigh much. But if you had let's say a rocket ship moving that fast or a missile moving that fast, then it would be carrying a lot more kinetic energy. So what? Let me take a look at that. Yeah, if two gases have the same RMS speed, then they must have the same average kinetic energy. This is false. It's answer key. Okay, then that was a mistake on the answer key. Sorry about that. Yeah, the correct answer for this is false. Uh-huh.
Question about 16, I was just a little bit confused how D was selected. I get A and E, that makes sense.
There are two ways to answer this question. One is you could just look at the acid-base chart is one. The other is just can it lose a proton and can it gain a proton? And so we'll look at the second way because the first way?
Yeah.
All right, we could do the first way.
Because I didn't see OH on the acid side of the chart. I might be blind, but I'm pretty sure.
Yeah, it's here.
Okay, but isn't that in the little section that kind of...
This little section is the very strong bases section. Therefore, its conjugates are extremely weak. So these bases, these acids here are in the strong base section, I should say. So these are the strong bases. So then the acids are extremely weak. Too weak. I'm not asking you if there's two types of questions here. One is can it act? The other is like will it act, right? And so these conjugate bases are so weak, right, up here that yes, they can act as a base, but will it, like chloride, will chloride neutralize anything? Well, it depends on how strong you react it with. In order to get these bases to react, you need acids that are much stronger than these.
So you consider anything that is on that side of the chart a Bronsted acid, no matter if it's not reactive or not?
Yeah.
Okay.
Yeah.
We have that drawn on the test.
Yes. So, right. Actually, so we would need extremely powerful base to get hydroxide to react as an acid. And those extremely powerful bases do exist. They're just not on this chart here. And what can happen is a powerful base can come over here and rip off the hydrogen as an H+ and leave us with oxide. That's one way to make oxide. I used to make this all the time, amide. And what I do is I used a very unusual base. I used sodium metal. but it wasn't like solid. It was sodium metal. Sodium metal dissolves in liquid ammonia, so I just cooled down the ammonia until it liquefied into a clear, colorless liquid, and then mixed it with sodium metal. Actually, I put the sodium metal in there first, then the ammonia, gaseous ammonia. Cooled it down. It just takes like dry ice. You could cool it down at dry ice temperature. Dry ice and acetone is what I used. Dry ice itself isn't a good thermal conductor, but when you mix it with acetone, the acetone doesn't freeze. It stays a liquid. And so you could use a dry ice ammonia bath, or dry ice acetone bath, excuse me, to liquefy the ammonia. And then the ammonia reacts with sodium, which is a powerful base, and then ammonia acts as the acid, oddly enough, and you can make sodium amide. So I used to make this stuff all the time.
Do you have this chart online?
Yes. Canvas. It's on Canvas.
Under which week?
I don't remember. It's on one of the weeks. Does anybody remember what week this is on?
I think it was like 6.
Week 6. Or just search Canvas for redox chart.
Where's the answer key for the exam 2?
Where's the answer key to exam 2? On Canvas, I think. Where did you find the answer key?
I don't know, was it in week 6? It was like week 6 or 7.
It's on Canvas. I don't know. Just if you hit the weeks, I posted it at the top of the week, not at the bottom. So if you just click on the week, you'll see it at the top. You don't have to look at all the other stuff if you don't want. You know, the answer key's there. What a lot of people do is, the first step in the scientific method is observation. So once in a while, people should look at this and see. There are some unusual species. And there are things that you wouldn't think are amphoteric, but are because they occur on both sides here. So it could be both, a proton donor and a proton acceptor. Now, like amide and oxide, those are not so common. Sulfides are very common. Methides, this is called methide. It's methane as an anion, so they call it methide, hydride, oxide, amide. Although people don't really pronounce it amide. Some people do. Most people pronounce it amide, sulfide. Here are all the ides. But these are not monatomic ides. Some of them, 3 of them are polyatomic ides. Polyatomic ides are kind of rare. But methide is very, very powerful base. People make it. People use it. They use it to do organic reactions. But what kind of acid would you need? What kind of acid you would need is something extremely powerful in order to get such a weak base to react. You'd need something more powerful than methide. So over at USC, there was a professor there who worked with superacids and superbases to get these unusual reactions to work. And this professor, Ola, he's no longer, I think he passed away, but he won the Nobel Prize in Chemistry for his work on superacids and superbases. So it can, when I say it can, it doesn't mean, for him and his research group, this was very common to get these extremely weak acids to react, extremely weak bases to react. All right, other questions? Uh-huh.
Maybe like 17 as well.
17?
No, never mind. I think, 25 when I did 25, I'm not sure. For the most part, but at least 90 yes.
Oh, 25?
Yeah.
At STP, it's 22.7 liters.
That's weird. I gave mine at like 24.
You're not.
Did you use 0 degrees C?
No, I used 25.
Oh no, the standard temperature for gases is 0 degrees C.
Oh, that's fine.
Yeah, that's why. If you use 25, then you're correct. Like 24.5.
Okay. So gases.
Yeah, this would be the molar volume of gas at room temperature and 1 atmosphere.
Gotcha.
Room temperature and 1 atmosphere are what we call just normal ambient conditions in the laboratory. 1 bar is a little bit lower than normal pressure. So I still use atmospheres. A lot of people do use atmospheres. So. All right, other questions? I posted a supplemental lecture on Canvas in the announcements section. And week 8 has it. Not the supplemental lecture, but the earlier question about where the keys are. It's week 8. Let's take a look at some of these here. I don't know, there's mixed. Some people want to use this as practice. Some people just want this as a study guide. You know, what do you want? Practice or like a mock test or just a study guide? Usually I don't talk about these because some people want to just figure it out themselves. But should I talk about it?
Post the answer key, and then the people that want to look at it can, and the people that don't want to look at it don't.
All right, that's fine. I'll do that. Answer key is already posted.
Are you going to mark which ones are we going to be looking at?
I did on the answer key.
Oh, yeah.
Yeah, but it's just chapter 7. That's it. But I do want to talk about some of these that cause a lot of confusion for people. And so I did post that. Did anybody watch the supplemental lecture?
Was the 27th one?
No, the longer one, hour and a half one.
You're going over exam 2, right?
No, not that one. There's another one. It was posted on the announcement section. Well, then, what I was going to talk about briefly today was related to that. I'll just talk about it. Yeah. Do you want to have to do calorimetry for everything? If you want to know how much energy is evolved or how much energy is consumed in a process, reaction, or object, do you want to have to do that? No, we don't want to have to do calorimetry. So we can make predictions, and that's ultimately what we want to do. And this is the power of thermodynamics. The power of thermodynamics is we can predict a lot of this stuff. And so temperature change, and then energy absorbed or emitted. So we'll just say heat lost or gained. This is for objects. And when we do these, if we ever need to know what the temperature change is or how much heat is gained or lost for an object, then these are the equations we use. Q is equal to mc delta T or Q is equal to the N, the number of moles, C delta T. This would be the molar heat capacity. This would be the specific heat. Or Q is just equal to the object, whatever object we're looking at, times C times delta T. So it could be a plate. We don't care how many grams the plate is. We just want to know how much heat or what the temperature rise in the plate is going to be. Or it could be a calorimeter, you know, or whatever. For reactions or processes, we look at this. The amount of heat, Q, is going to equal the amount times delta U, or Q is equal to the amount times delta H. Now, this depends on how we do the reaction, and so this is part of the supplemental lecture. This is what we call QV. QV stands for constant pressure, constant volume. And this is for QP. This is constant pressure. So what we're doing is something called, today we're doing, this is what we call bomb calorimetry. This over here is coffee cup calorimetry. And so why do we have to use a bomb? This is kind of the anti-bomb calorimetry. You don't want a bomb, therefore we have to use a bomb. Why do we use a bomb? Yeah, it has to be strong because it has to withstand expanding and contracting gases, right? If we form a gas, it's going to expand into the container. So it has to withstand large pressure changes. And so we don't want it to explode and we don't want it to implode. However, sometimes they are equal. Sometimes QV and QP are equal. Like in our lab, we can do this in the coffee cup, but even if we did this in a bomb, would you expect a pressure explosion by mixing hydrochloric acid and sodium hydroxide solution? No. And so for our lab, QP and QV are the same. But technically, when we're dealing with a QV, the amount of energy associated with that is delta U, the change in internal energy. However, when we're dealing at constant pressure, we use a different symbol for this. We use delta H. Delta H is the energy change associated with things at constant pressure. And so all we're doing today is this. We're just determining the delta H. We're determining the delta H of sodium hydroxide dissolution. The delta H is going to equal Q P from the calorimeter. And so we're doing calorimetry to measure the amount of heat. The way we're going to get the Q for sodium hydroxide dissolution, this is QP, constant pressure. But in this case, it doesn't matter. QP and QV are equal. For sodium hydroxide dissolution, divided by the amount. And we're going to do the amount in two ways. We're going to do it per gram and per mole for the amount. So per gram and per mole. So we want to know how much heat is evolved for every gram of sodium hydroxide that dissolves, and then how much heat would be evolved for every mole of sodium hydroxide. A mole of sodium hydroxide is like 40 grams worth. So it'd be 40 times as much energy. And where we get that heat is from the surroundings. You know, cue the surroundings. If you recall, what were the surroundings in this? Minus Q the surroundings. That was Q of everything left over. Except for the calorimetry. The calorimetry we treat separately. Q the calorimeter. I.e. the solution. And then we could get that. So we're after the delta H of sodium hydroxide dissolution. So once we have this per gram, we can predict it. If I had 10 grams, how much heat? If I had 30 moles, how much heat? And so delta H is extremely useful for calculations, for predictions. And so this would be called the enthalpy of sodium hydroxide dissolution. We call it the enthalpy of, and this one, P. P stands for what? Pressure? This is one of the things you have to keep track of in thermodynamics. You have to keep track of the conditions you're doing it under because it gives you different amounts of heat. In this case, it gives us the same amount of heat, but in other scenarios, we get a different amount of heat. We have to be careful about it. And therefore, we always need to keep track of how we're doing it. All right, so that was the first calorimetry experiment we're going to do today. The second calorimetry experiment we're going to do is delta H of, or was that? No, that wasn't the first, sorry. First one was hydrochloric acid. That was the second one. Got mixed up. This would be experiment 3. Experiment 1 was calibration of the calorimeter. This will be experiment 2. It will be HCl sodium hydroxide. This is HCl aqueous, sodium hydroxide aqueous, neutralization. And so we call this the enthalpy of neutralization or something. And so we need Q sub P of neutralization. We're doing it under coffee cup conditions over the amount. This one, we're going to do the amount of limiting reagent. What was the limiting reagent again? Sodium hydroxide. And how many moles was that? Mm, 0.0500 moles. If 0.0500 moles of sodium hydroxide reacts, then 0.0500 moles of hydrochloric acid reacts. And so we could just say per 0.0500 moles and then divide it, and then we get it per mole of reaction after we divide it. This one we aren't going to do per gram. It makes no sense to do it per gram. And so this will just be in per mole. So again, the QP of neutralization, we're just going to get that from calorimetry. That's just going to equal minus Q of the surroundings, which is equal to minus Q of the leftover solution. The leftover solution is going to be 100, or was it? No, 50 mils? I can't remember. Let me leave that off. Plus Q, the calorimeter. And so, again, once we know delta H, then we could predict how much heat is going to be released for any number of moles of reaction. You know, so if we had 10 moles of reaction, whatever. And so delta H's are extremely useful. And in this case, delta H would be the same as delta U. In experiment 4, we're going to look at delta H of HCl aqueous plus sodium hydroxide solid. And so for this particular experiment, we can't add the acid. But in reality, it's not a big deal because the acid is so dilute. If this were highly concentrated acid, then I'd worry. You know, for example, if this were 12 molar HCl or something like that, then yeah, I would be concerned because this is solid, pure sodium hydroxide we're adding. And so it could generate a lot of heat and cause a little bit of a violent reaction here. And so this is going to be equal to Q of what we call Q sub P of neutralization over the amount. So now what we have to do is, in this case, we could do it per gram. This is the limiting reagent here is going to be the sodium hydroxide. This would be the LR. And so if sodium hydroxide is the limiting reagent, then we could do it per gram of sodium hydroxide and or per mole of sodium hydroxide. Actually, we're going to calculate both per mole of sodium hydroxide here. And so both of these are very useful, either per gram or per mole, for prediction, for calculations. And so this is the same thing. This is just minus Q, the surroundings, which is going to equal minus Q of the product solution plus Q of the calorimeter. I wrote the equations for this last time. All right, now we're going to, once we get that data, then we can use this data. There's something called Hess's law. And the objective of Hess's law is to determine, you know, the main application is to determine unknown delta H's from known delta H's. So that we don't have to do another calorimetry experiments. I'm sorry?
Could you scroll up for just a second and leave them in?
Yeah.
A little bit more. Yeah, down a little bit.
Okay. The goal is to not have to do too much experimental work. The goal is to be able to predict these things. These calorimetry experiments are difficult. And so if we use Hess's law to predict, then we've just saved ourselves a lot of work. And so if I have just some generic reaction, AA plus BB goes to CC plus DD. Actually, I should go GG plus HH. But we'll just go with that. And so let's say I know this is delta H for reaction 1. If I reverse this, let's say I go CC plus DD goes to AA plus BB, then we know about the first law of thermodynamics. So delta H of the reverse is just equal to negative delta H of the forward. And so I wouldn't have to do another calorimetry experiment if I was looking at the reverse reaction. If I multiply the reaction by N, so let's say I double it or triple it or cut it in half, then delta H of N times is just going to equal N times delta H of the original. And finally, what I can do is, if I have an unknown delta H and I can get some reactions to add up to give us the same. And so this is the main Hess's law here. That is, delta H of reaction is equal to the sum of the steps. So if I had delta H of 1 plus some other reaction, delta H of 2 plus etc., then I can just say that if I can sum up the steps to make it equal the same reaction, then I can predict it that way. So I look for equations that will add up. And so in our particular experiment, that's what we're going to do. We're going to look up the sum of the steps. So let's take a look at what we're after here. So what we're after is this. We're after delta H of 3. Is this it? No. Yeah, well, in this particular example, we're after delta H of 3, but it turns out delta H of 1 and delta H of 2 add up to give us delta H3. So we just combine the two energies there. Let's see what we're after in this particular experiment. So this kilojoules here is just Q, and then we just divide it by the amount. In this case, the amount in moles. I thought we were going to do grams, but it looks like we're not. All right, so number 5, let's say, using Hess's law, calculate delta H for the reaction in number 4 above using delta H values calculated in number 2 and number 3. Assuming this Hess's law calculation is correct, the theoretical one, calculate the percent error in number 4. And so actually we're going to do it for both. This reaction, we're going to use Hess's law to predict what delta H should be based on the two equations that add up. And then we actually did this one with calorimetry. Here it says assume, this one I don't like here. It says assume it forms 52 grams of solution. They're going to tell you, they're probably not going to give you 2.00 grams. They might give you like 1.98 or 2.02. If that's the case, use the grams you got. So it's 50 milliliters of water or 50 milliliters of acid plus 2 grams of sodium hydroxide. But if they don't give you 2 grams, then let's say they gave you 1.9 grams, then it would be 51.9 grams of solution, not 52 grams of solution. The same thing goes when we had the solid sodium hydroxide here in number 3. Again, it might not be 52 grams. Just use the number of grams they gave you. It could be, but sodium hydroxide is such a pain to weigh because of it. It's so hygroscopic. It loves to absorb water, and so it's hard to get a reliable weight. And so that's why you see this weight is only to 1 decimal point. It's only to 1 decimal point because it's probably already in error. But we could add up equation 1 with delta H1. This is delta H1 here. And we could add up equation 2 with delta H2. And if they just add up in a 1-to-1, then we get 2 ways to determine delta H3. 1, Hess's law. We just calculate it, write it here. 2, calorimetry. We just write the answer from calorimetry there and then compare. And they give us a theoretical value for this here, and so we could see how close we are. So we're going to determine the percent error from calorimetry and the percent error from Hess's law. All right, any questions on this? All right, I'm going to stop talking here. So again, this today we're working with sodium hydroxide, which is an eye hazard. And so you'll have to be careful. If your skin feels slippery, don't rub your eyes, because that means you have sodium hydroxide on your skin. Sodium hydroxide can cause severe eye damage. We're using solid sodium hydroxide, which is like pure. So be careful with that. Also, try to take a look at the supplemental lecture.